direct substitution with this problem here. And I'm going to have kind of an arrow because I'm going to look at the numerator and the denominator separately. You have to be careful on this particular problem not to write what we're going to get as an answer. What happened to my arrows? And I'll explain why after we take a look at it. Oh, there's lovely arrows. All right, so we have 2 squared minus 4. Well, that's going to be 4 minus 4, and that's 0. So the numerator there is going to 0. Let's how about the denominator? Well, we have 2 minus 2, and that's equal to 0. Both the numerator and the denominator are going to 0. So we can't use direct substitution. So both the numerator and the denominator approach 0. Now here's a little important, very, very important for the AP test. In the past, it had been fine to write 0 equals 0, and then we realized, oh, we have to do something else. But you don't write that the limit equals 0 over 0, because technically this is untrue. It's called a link. Numerator, that limit's going to 0, and the denominator, that limit's going to 0. What we have here is what's called an indeterminate limit, and that should be a T. Indeterminate limit. And basically what that means is we can't determine anything about the limit from our answer. We need to do more work. And we have an answer that we can't know anything about. Can't determine a single thing about this limit. Right? So when you realize if you plug in, or afterwards if you realize you plugged in you have 0 equals 0, be careful, don't write 0 over 0, just write that the numerator is going to 0 and the denominator is going to 0, and then you never will have said something untrue about the limit. Because our limit is technically not 0 over 0, which has no meaning. Our limit is indeterminate. So we're going to do some work and determine something about our limit. All right, so if we were to use a graphing calculator, and I can show you this in class, right? And so maybe we'll take a look at it. We plugged in the value, -2. Of course, we can get a lot closer than that. And we were to scroll closer and closer and closer to 2. We would find that we have an error at x equals 2. 2, that is undefined. So f of 2 does not exist for this particular function. All right? But if we do something, we can find the limit. What we need to do, since we're getting 0, the numerator is going to 0, I shouldn't even say. That's been called bad now. Since we're getting the numerator approaching 0 and the denominator approaching 0, it means that our numerator and our denominator share a root. So this means we should be able to factor and reduce. Right? Well, x squared minus 4, that factors to x minus 2 times x plus 2. And now we see, oh, look at that, we could cancel out the x minus 2's. And now we have the limit as x approaches 2 of x plus 2. Right? And that we can substitute into, right? That would just be 2 plus 2 or 4. Right? So remember, a limit is where the function is heading as it approaches a value from the left and the right. At 2, there is a hole in the function. Matter of fact, this looks just like a linear function if we graphed it, with a hole in it at 2. So therefore, x never equals 2, but the function can approach it. So it never equals 2, but it does approach it from the left-hand side and the right-hand side. All right, so finding the limit of the function. So often the direct substitution method does not work. So we need to be able to algebraically manipulate and simplify expressions to make the determination of limits easier, or even possible. And so here, if we were to plug the 1 in, right, so the numerator would go to 1 cubed minus 1. Well, 1 cubed is 1, and 1 minus 1, that's 0. And the denominator, that's going to 1 minus 1. That's also going to 0 as x approaches 1. So this is another indeterminate limit. So we can't just substitute into our function here, our equation here, to find the limit. We're going to have to do some reducing. We have a common factor that needs to be factored out. Now, maybe you remember how to factor this. What if you forget? Well, you could always use substitution, right? Synthetic division, right? And be able to rewrite your equation and factor it that way. Right? So I'm going to do it both ways in case you forget. All right? So since we're getting 0, right, when we plug in 1, it must be that x minus 1 or 1 is the problem. Right? So the number you're trying to plug into, right, that must be the problem, right? And so they must share x minus 1 as a factor or 1 as a solution. Right? So if you didn't remember how to factor this, and I'll show you in a moment, right, you could just say, okay, 1, 0, 0, 1, right, because we have no squared term, we have no x term, right, and then use synthetic division. So you'd bring down the 1, you'd have 1, you'd add, you'd have a 1. Oh, excuse me. That's a negative there. Multiply 1 times 1 is 1. You'd add, you'd have a 1. 1 times 1 is 1. You add, you have a 0. Right? And so that gives you the second equation there. So that's x squared, that's x, and that's our constant. Or you could remember the pattern, right? Either will work, right? So if for a something cubed, just call it a cubed, minus another something cubed, let's just call it a b cubed, right? When you factor that, that's going to be a minus b times a squared, and this time it's going to be a plus a times b, and then plus b squared, right? But if you forget that, no big deal. You could just use synthetic division here. You know what x minus 1 has got to be a factor, right? So it's not even like you have to work really hard for it. All right, so let's rewrite this. So we have the limit as x approaches 1. Now we're going to have x minus 1 times x squared plus x plus 1 divided by x minus 1. Oh, there's our problem. It's that nasty little x minus 1. We'll cancel that out. We have a hole, right, in our graph at 1, right? So there is a hole at x equals 1. Now our new function, our new rewritten simplified one, so even though x can never equal 1, we can still find the limit as x approaches 1, because now we can substitute into x squared plus x plus 1, right? There's no problem now. No way that could have a 0 in the denominator. It doesn't even have a denominator. Right? So our limit is, our function is approaching, or our limit as x approaches 1 is 1 squared plus 1, and that's going to be 3. Right? So there is a hole in our graph at 1, 3, right? But we're approaching 3 from the left-hand side and the right-hand side, because we could substitute now. Right, so indeterminate form, when you cannot determine the limit by substituting. Some of its form? Let's put an S here. All right, so remember, just don't write 0. These are the big ones. Don't write these. Okay, the AP board doesn't like to see that because it's technically not the limit, right? So instead, just do what I did. So approaches 0, approaches 0, approaches infinity, approaches infinity, and the same thing with negative infinity. So let's just put plus or minus. For those three, just write it like this, and you won't have a problem. The other ones are okay. Oh, and this, by the way, is a comma, not a 1. That's a big comma. We'll talk about the other ones later. As a matter of fact, right now, we're only going to be dealing with one of them, and that is this one, that 0 in the numerator, numerator going to 0, denominator going to 0. But these are some of the other forms, and you'll need to know those. Right? So it could be that the numerator goes to 0, the denominator goes to 0. The numerator grows without bounds, and the denominator grows without bounds. The numerator decreases without bounds, and the denominator decreases without bounds. We have one term, so 0 over infinity doesn't mean one of them is 0 and the other one's infinity. That, first of all, it would be impossible for a number to be infinity. What it does mean, and it doesn't even mean that the other one is 0. And you might say, oh, 0 times something, that's 0. Well, it's not 0. What it means is that something is getting very small. So it's getting very small, not decreasing without bounds, just getting very, very small. Like maybe 0.00001, that's very small. And this one is getting very big. So there's a problem. One's getting small, one's getting big. Who wins the war? Right? Which one wins out? Does the function get very small faster, or does it get very big faster? Because that's going to determine our limit. We'll deal with those in a later lesson. Here again, we have 1 raised to a power. Right? Well, we know if we raise 1 to a power, right? Any power, we're going to get 1. Right? But here, this isn't exactly 1. This is something that's close to 1, very close to 1. And we're raising it to a very large number. Is that large number, is it large enough to beat out the 1? Right? Same thing here. Close to 1 means there'd be no change. Very large. Who wins? And now we have something very large minus very large. And it's not 0 because one of them might be larger than the other. Who wins the war? We'll have ways to deal with all of those. Let's just look at the first one. All right, so for all x values other than, here's our function. Here's our function back again. So for all x values other than 1, the functions f and g agree. Right? So here on the right-hand side, we have the graph f g of x equals x squared plus x plus 1. On the left-hand side, we have f of x equals x cubed minus 1 divided by x minus 1. Notice we have a hole. There's a hole in our graph right there at 1, 3. And we found out by simplifying this, right? Remember we factored and then we substituted in, that from the left-hand side and the right-hand side, you can see from the graph we're approaching 3. And algebraically, we had found that from that our limit was indeed 3. And I won't solve it here because I could just easily go back here. Maybe I'll solve it there before I post this, but I could just do this and show you, yes, it was 3. Right, so we want to find the limit. So here, this would be the way to write that. This would be appropriate, where we have these arrows. The numerator is going to, the denominator is going to. Everyone will be happy with that. All right, so here we're taking a limit of a rational function. All right, but if you try to plug a -3 in, right away you can see there's a problem in the denominator. And that makes you think, is there going to be a problem in the numerator? So we look. Oh, as we plug in -3, the numerator, you'd have -3 squared, that's 9. 9 minus plus a -3, that's 6. 6 minus 6, that's 0. So the numerator is going to 0. The denominator is obviously going to 0. So direct substitution fails, but don't need to worry. because the limit of the numerator is also 0, the numerator and denominator have a common factor of x plus 3. If just our denominator was 0, well, we'll talk about that. We'll wait, and I'll talk about it. Notice I have a little note here, next page. I have a feeling I gave myself space on the next page. There we go. And a little reminder, do not drop the word limit until you substitute, right? Otherwise, you have a linkage error. You've said something untrue. Because remember, the function x equals negative 3 is not going to be in the domain of this function, ever. However, the limit will exist, right, as x approaches negative 3. So keep limit until we substitute. Because the function is never negative, or x is negative 3 for this function. All right, so we want the limit as x approaches negative 3. X squared plus x minus 6, it could do factor by grouping, but I think that maybe because this is a pretty easy one, you might recognize that that might be x plus 3 and x minus 2. Right? Two numbers, right? We have the a term is 1, right? So we have we're going to have a x as the first term in both the binomials there. So all we have to do is figure out two factors of negative 6 that are 1 apart. Hey, it's 3 and negative 2. Right? And we know that x plus 3 must have been 1, right? Because we have a common factor in the numerator and denominator, and the denominator only has one factor. Now we see I can cancel those out. Right? Still, don't drop the words limit. So we have the limit as x approaches negative 3 of x minus 2. Now when you're ready to substitute, now you can drop the limit. Right? Not until that point. Right? So it's just going to be equal to, I'm going to plug in the negative 3. Negative 3 minus 2, that's going to be negative 5. Right? So from the left-hand side and the right-hand side, right, our function is approaching negative 5. Never reaches negative 5 because there's a hole at negative 3, negative 5. Right? Let me write that down. There's a hole. We can tell on this one there's a hole, right, because I canceled out a factor in the numerator and the denominator. So our hole is at negative 3, negative 5. However, the limit still exists, right? Because we're approaching the same value from the left-hand side and the right-hand side. I didn't do a graph of this one, I don't think. Because we were able to reduce and we can substitute, the answer we get, that is indeed our limit, right? So we have a hole at negative 3, negative 5. But the limit of our function here does exist just because the point doesn't exist, right? So f of negative 3 does not exist because of that hole there. But the limit as x approaches negative 3, I'm just going to put f of x, does exist, and that's negative 5, right? So make sure you don't confuse the function, a point existing for the function, and the limit existing. Those are two different things. I do have a graph of this one. Good. I had forgotten. I do so much, sometimes I forget. So notice here from the left-hand side, so our limit as x approaches negative 3 of, I'll just put f of x so I don't feel like writing the whole thing again. And it says f of x, so it is okay. Right? So if you have a function labeled f of x, feel free, or g of x, or whatever it happens to be labeled, feel free to just write f of x, right, instead of writing the whole thing. At least when I want to label something like this. Right, so the limit of f of x as x approaches negative 3 from the left-hand side is negative 5. And then if we look from the right-hand side, we see the limit of f of x as x approaches negative 3 from the positive side is also negative 5. Right? So our left hand and our right hand limits agree. Therefore, the limit exists. It doesn't matter there's a hole, right? Because we're approaching the same value. And the limit is not about what the function equals, it's about what the function approaches. All right, so if we try to substitute in the, let's check out. So I'm going to use little arrows there. We've had so many that have just failed for us. By the way, I don't know what happened to this when I typed it, but it's x approaches 2 and it's way up there. All right, so Let's see if it's okay. All right, so if the numerator is going to 2 times 2 squared minus 5 times 2 plus 2. Well, 2 squared is 4 times 2 is 8. 8 minus 10 is a negative 2, and negative 2 plus 2 is 0. What's the denominator going to? So we have 2 cubed minus 2 times 2 squared minus 2 plus 2. All right, so 2 cubed is 8, and so is 2 times 2 squared. So we've got 8 minus 8, that's 0. And so negative, then we have 0 minus 2, that's negative 2 plus 2. Oh, that's 0. All right, so this is an indeterminate limit. We don't know anything based on that answer. Except for one thing, because this is a rational function, there's got to be a common factor in the numerator and denominator. That is the only thing we do know. All right, so we have, let's factor this, the limit as x approaches 2. All right, and over here on the right-hand side, I'm just going to factor these. All right, so 2x squared minus 5x plus 2. 2 times 2, that's 4. So we want two numbers that multiply to give us 4, but add to give us a negative 5, must be negative 4 and negative 1. Right? So 2x squared, come on, writing. There we go, minus 4x plus, it's really hard to write when I can't see where my numbers are. Oops. I may also put everything in and then put my parentheses in. Negative x plus 2, and the first two are a group and the second two are a group, and we'll factor out a 2x, and we'll be left with x minus 2. We'll factor out a negative 1. It'll be x minus 2. So all factored, we have 2x minus 1 and x minus 2. Denominator is perfect for factor by grouping. I'm just going to automatically put the parentheses in. X cubed minus 2x squared and negative x plus 2. Look at that. They just look like they go together, don't they? All right, we'll factor out an x squared, so that's x minus 2. Factor out the negative 1, x minus 2. So we have x squared minus 1 times x minus 2, which is x minus 1, x plus 1, x minus 2. There we go. Now we'll rewrite it. So we have the limit as x approaches 2 of 2x minus 1 times x minus 2 divided by x minus 1 times x plus 1 times x minus 2. And there we see the problem. Well, if the numerator and the denominator of an x minus 2, that's causing a problem for us. So remember to keep the words limit. We have the limit as x approaches 2, 2x minus 1. I'm not going to multiply those together. I'm just going to leave them as x minus 1 times x plus 1. Why not? Just as easy. All right, and so now I'm going to substitute. So now I'm dropping the word limit. So we have 2 times 2 minus 1 divided by 2 minus, oops. That's not a very nice looking subtraction sign. 2 minus 1 and 2 plus 1. All right, so that's going to be 4 minus 1, that's 3. In the denominator, I've got a 1 times a 3. I'll write it in. Right, so that's just going to be 1, right? Because the 3's would cancel. Right, and so the limit as x approaches 2 is 1. F of 2 does not exist. However, the limit does. I think I'm very close to the end of my Nearpod. All right, so let's find this one. Right? Limit of 2x plus 5 over x minus 2 as x goes to 2. All right, so now look at the numerator. Look at the denominator. Let's look at the denominator right away. All right, we see 2 minus 2. Well, that's going to be 0. How about the numerator? 2 times 2 plus 5. Well, that's 9. That's not 0. So that means that our limit is going to be 9 over 0. That's not indeterminate. It's not 9. It's not 0. It does not exist. All right? Asymptote in the denominator, not a whole. All right? So, in this case, not an indeterminate limit. The limit just does not exist. Right? We've got, this would be a rational function. Kind of looks like this. It's going to have a, and this is very crudely drawn, would have a horizontal asymptote at 2. So pretend that's at 2. There we go. And it'd have a vertical asymptote also at 2. Right, so there's this vertical asymptote. It's probably should do a dotted line. And then it's going to look like this and this. Right? So as we approach 2, one side's going to negative infinity, one side's going to infinity. Not indeterminate at all. It just doesn't exist. So let's take a look at 3 scenarios here. If the limit is a constant over 0, then it's equal to does not exist. Make sure this is in your notes. It says notes. I think I left a blank space for you. If the limit is 0 over a constant, this time it's not does not exist. It's just 0. If the limit is 0 over 0, or remember, we're not writing 0 over 0. We're just writing, right, this way and this way. But for the simplicity of me being able to write it here, and it's going to be, where's my box going to go? I don't have any place for my box. I don't think my board's going to like me pushing it down so far. Oh, it's okay. It's going to do that. All right, so if we have a 0 in the numerator and a 0 in the denominator, that's an indeterminate limit, and we need to simplify algebraically. All right, so here's our 3 scenarios, and they all mean different things. All right, so if you have any questions, let me know. I think that was the end of my podcast. And so here I have some problems for you to do in class, and I'll post them as well as show you these problems in class. All right, thanks for watching. Bye for now.